Solve a problem so clearly, it's like applying to a window index. This is 27070, maximum number of jumps to reach the last index. Oh, I have to sneeze. Woo! That'll wake you up. Okay, so you're given a zero indexed array nums of n integers and an integer target. All right, so you have an array nums and you have some value target. Let's just say, for the sake of trying to figure out what this array kind of looks like, maybe it has some elements, and it has some other last element, and it's of length n. So that's the length of the array, n. You are initially positioned at index 0. All right, so this is something to do with positions relative to arrays. So I'm positioned here at index 0. We'll call that my I position. That's where I begin. And in one step, you can jump from index I to index j such that 0 is less than or equal to I, less than j, less than n. So what does this first condition imply about the nature of how I can jump? Well, if I'm starting at index I can only go from I, less than j, less than n. So I can go from I, less than n, to j, less than n. Well, these outside boundaries just mean I can only jump, right? I can only jump within the range of the array, right? I can't go outside of this boundary because I can't go less than 0. And I can't go outside of this boundary because I can't go less than n. I can't go greater than n, right? I can't go in a position that's greater than n. So that's kind of what these outer boundaries imply. What about this I and j? Well, this implies that I have to move forward. And I have to move forward. I can't move backwards, right? If I'm at I can only go to a j such that j is greater than I, right? So if I'm here, for example, there's no way that I'm going to be able to go back, right? The only thing I can do is go forward, right? I have to go to a position that's greater than the current position that I'm currently at. And also note that it's not less than or equal, so I can't jump to the same position. So I always have to be jumping forward, okay? So that is the first condition. The second condition states that negative target, so this target that we're given, has to be less than or equal to nums j minus I less than or equal to target. So this is just a weird way of saying that, nums of j, right, minus nums of I, if we would take the absolute value of that, has to be less than or equal to, right, target. Okay, so what it's basically saying is if I want to jump from I to j, the difference between those two things needs to be less than or equal to target. Okay, now so that might be a little confusing, but it's like if I want to jump from C to, or let's say I'm at B, right? Let's move these two. If I'm at B and I want to move to D, well, I can only do that if the value of this D minus B, so if D minus B, the absolute value of that is less than or equal to target. Okay. Now, given that situation, we want to return the maximum number of jumps you can make to reach the index n minus 1, right? So, of course, if this is length n, then n minus 1, right? You would start here at 0, and you'd want to end at this last index here in this array at n minus 1. Okay. If there is no way to reach index n minus 1, return negative 1. So that could happen, right? What if, you start at a position that's gigantic and you need to get to a position that's, very small at the end and the target value is very small? Well, you're not going to be able to reach it. If that doesn't make sense, I'm guessing there's probably right here, right? So if the target is 0, that means the difference between each, ij pair has to be 0. So the only way you're going to get from 1 to anything is if the difference is 0. So the only difference is 1 itself. So you can only get here. You can never get to this 2 because you can never get a target equals 0 to, get a difference of 0 to get to 2. So there's no way to traverse the system. You can walk through it given this second condition, right? This second condition here. All right, so let's actually, oh my God. Let's put things where they need to be. Not where they need to be, but where they can live for now. Okay. And this is, this is condition 1, this is condition 2. Okay. So let's go through an example. Okay. So in this example, we have nums equaling 136, 136, 412, 412. And then we'll just comma separate them. And then we have target equaling 2. Now, I'm going to draw this in kind of maybe not completely intuitive way, only because that's going to help us solve the problem later. So I'm kind of preemptively doing some notation here, which may not make sense to you now, but just understand that in a moment it will. But what I'm going to do is I'm going to draw this system as, you know, essentially a set of nodes, okay? So I'm going to convert these things to nodes. So I'm going to have node 1, node 3, node 6, node 4, node 1, and node 2, right? Now, for this problem to work, right, like we're trying to find the maximum path, but we can't just jump to any node that's in front of us, right, given this condition with target. So for any node, there's going to be a set of nodes that it can travel to, right? You know, if the target is 2, then 1 can only travel to certain nodes that it come after, right? Only if the difference between them is 2. So 1, for example, can travel to 3 because the difference between them is 2, right? 3 minus 1 is 2, so the difference is 2. It's less than or equal to target. 1 cannot travel to 6, right? Because 6 minus 1 or 1 minus 6, the absolute value of that is 5, which is greater than target. So 1 can't travel to 6. 1 can't travel to 4 because the difference is 3. 1 can travel to 1 because the difference is 0. Right? And it can travel to 2 at the end because the difference is 1. And now we can play the same game for 3, right? So 3 can travel to 4. I'm just going to go through quickly now because I think you get the idea. 3 can travel to 1. And 3 can travel to 2. 6 can travel to 4. And that's it, right? 4 can travel to 2. Now, I may have messed something up here, right? But this is kind of the system if we thought about it in terms of like nodes and edges, right? Or vertices and links between the vertices, right? We start here, and these are all the paths that we can take. So what we want to do is find the path that results in, you know, I forgot about this one can attach to this too here, right? You always forget some. But these are all the paths that you can take within this system, and we're trying to find the path that is maximum, right? So each of these edges corresponds to a jump. So we want to maximize the amount of time that we're in the system, right? We want to maximize the number of jumps. Now, just eyeing it, you know, we could say, well, we could start here. If we went here, that'd be 1 jump. This would be 2 jumps, 3 jumps, okay? We could do 1 jump. No, we don't want to do that. We could do 1, 2. We could do, we could literally just iterate through all of these jumps. We could go 1, 2, 3, or 1, 2. Right, so there's a bunch of paths, right? There's an insane number of paths, you know, and it would be very inefficient to solve it this way. But, you know, just eyeing this, it looks like the answer is 3, right? Because you go 1, 2, 3, or 1, 2, 3. So 1 to 3, 3 to 1, 1 to 2, or 1 to 3, 3 to 4, 4 to 2, right? And that's the answer 3. This has the 0 to 1, 1 to 3, 3 to 5. So 0 to 1, 1 to 3, 3 to 5. So that's this path, right? It's doing it by index, not by value. Yeah, that results in the answer. So you can kind of think of it as this graph, but as it can be seen just by kind of reasoning through this, right, it's going to be very inefficient to like try to exhaust all paths, right? That's one possible thing you could do. You could take this system, you could draw it out, you could find all the edges that connect everything, and then you could exhaust all possible paths. But that's probably not going to be efficient enough given the constraints. But what are the constraints? Well, for this problem, we have nums of length equals n less than or equal to 1,000. Now, constraints can be misleading, but they do tell you something about the nature of the problem, right? They tell you what something can be, but not necessarily what something is. And what I mean by that is like, if n is less than or equal to 1,000, right? That's 10 cubed. So n squared, 10 to the 6, or yeah, 10 to the 6 would be an acceptable solution, right? Because in Leetcode, at least, anything that's like around 10 to the 6 or less, right, in terms of the runtime, right? So if n equals 1,000, that means, you know, I'm trying to, just as a kind of a side note about constraints and how they can really help you solve problems, okay? So if n equals less than or equal to 1,000, that means that in the worst case, n equals 10 cubed, right? So then if we had a big O of n squared problem, that would be, you know, 10 to the 6. And Leetcode allows you to do anything. Leetcode will almost always pass a solution that takes 10 to the 6 or less time in order to operate, right? Less than or equal to 10 to the 6, it works just fine. So if you find a solution that, you know, when you look at, okay, n is less than or equal to 1,000, okay, that's 10 cubed, 10 squared, 10 to the 6. If your solution is less than or equal to 10 to the 6, you're probably good to go, right? But not necessarily, right? If a problem is inefficient, then this value has to be small, right? But it's also possible that this value is small, yet the problem is still inefficient. Okay, so there's kind of like a directional relationship between the logic there, right? If the problem's most optimal solution is extremely inefficient, then the constraints have to be small. But if the constraints are small, it doesn't necessarily mean that the problem has only and exclusively inefficient solution, right? So just because this value is small doesn't mean that necessarily the solution will always be inefficient, like n squared, you know, compared to n or log n or whatever. But if the thing was inefficient, it would have to be small. So hopefully that makes a little bit sense to you guys. I don't want to ramble too much because it's kind of a side note, but, you know, maybe I should make a video about constraints and how they can help you, right? Because they can be a really good indicator about the nature of the solution or what will pass. But all that's to say that, you know, maybe there is something more efficient than n squared, but n squared will work for this problem. Right? If we solve this problem in n squared time, it's going to pass because it's approximately 10 to the 6, which is, you know, within the boundaries of what Leetcode will accept in terms of, you know, compute. You won't get a time limit exceeded error. All right, let's continue. So, boom. So when we look at this, how are we going to solve this using this idea? Well, you know, I guess what I always struggle with when I explain these problems is, do I explain it, you know, in a traditional data structure and algorithms way, or do I try to explain it more, you know, in a, not intuitive, but in a manner that is less technical and more just observational? Well, you know, the technical way of explaining this would say, well, if you look at this situation, right, this is a directed acyclic graph, okay? This is a very technical explanation of how to solve this problem, which means that there's no cycles and the system is directed, right? There's an edge going from 1 to, you know, from 1 to 2, but there's no edge going, but this same edge I can't take back, right? This has direction built into it. I can jump from 1 to 2, but I can't jump back from 2 to 1. Right, so it's a directed edge, right? This edge has direction. It has to be, in order to use this edge, I have to start here and I have to end here. Acyclic means there's no cycles in the system, right? Which there can't be because I always have to jump forward, right? So since I always have to jump forward, I'm never going to be able to jump back to complete the cycle, right? If I go from 1 to 3, I'm never going to have a chance to go back to 1 because I'm always jumping forward, right? And then this is a graph, right? Because there's nodes and there's vertices. So if you have a directed acyclic graph, right? Whenever you look at a problem, right, you say, okay, I have they call them DAGs, right? If I have a DAG, this can always be solved with dynamic programming, okay? So that's the kind of technical way of looking at this, right? And modeling it as a graph and then saying, oh, look, this is directed acyclic. That means I can solve it with a DAG, right? And that means for any node, right, X, how you would solve this is you would look at any individual node, like 4, for example, right? And then you would look at all the people that can get to 4, and your solution would be just a solution based on theirs, right? The solution, the solution at 4, right, if we're trying to maximize our length, right, is, well, the solution at 4, the node 4, is just 1 plus the solution at node 6 the max of the solution at node 6 or the solution at node 3. Right? The best path D is the best, so let's call D equals longest path to node X. Okay. So D of X equals the longest path to node X, right? So D of 4 is the longest path to node 4. Well, that would be, well, then it's just, well, what's the longest path to node 4? Well, it's going to be 1 plus all the nodes that can get to 4. If that makes sense, right? What I'm basically saying is the longest path to get to 4, well, I'm going to have to jump at least once to get to 4, right? So that means the longest path to get to 4 is 1 plus all the things that can get to me, right? Either I took this 6 path or I took this 3 path, right? So the longest path to get to 4 is 1 plus whatever the longest path is that I can get from my neighbors, right? So the longest path to get to 4 is the thing 1 plus whatever the things are that can reach me. All right? So that's true for any node, right? So I could do that for 1, 2. So in order to solve this problem, I guess generally, right, is what we would do. Oh, I lost whatever that was. 6, 4. Right? If let's say that when I labeled these things green, that means that I solved them, right? So I'd say the longest path to get to 1 is 0, right? The longest path to get to 3 is 1 plus whatever the paths are that I can get to 3. So I'll label these 2. So the longest path to get here is 0. The longest path to get to 3 is, well, 1 plus all the things that can get to me. Well, there's only this 1. So 0 plus 1 is 1. And then when I look at 6, well, it's 1 plus the paths that can get to me. Now, this is kind of an exception case, right? Because there are no paths to 6. So there is no 1 to add. So this would also just be 0, right? And I guess the idea here is, well, I'm adding 1 when I use these edges, right? If you want to think about it like that when you traverse this system, right? I'm adding 1 when I use these edges. So the path to get to 6, there's no 1 to add, right? There's no 1 to add by using edges. So the length is 0. When we look at 4, so let's look at 4 now. So 4 is going to be 1 plus this path, which is 1, or 1 plus this path, which is 0. So 1 plus 1 is 2, 1 plus 0 is 1, so the best here is 2. Okay, and then when we look at 1, okay, well, what are my paths? I could do 1 plus 0 to get 1, or I could do 1 plus 1 to get 2. So obviously the best thing to do here is 2. Right, and then when I highlight these, it means that they've been solved, right? So I know the value for those systems. Now when I get to this last one, it gets fun, right? I could do 1 plus 2 to get 3 here, so I do 1 plus 2. So I do 1 more than, well, how long did it take to reach this neighbor? Well, I've already solved that, and that's 2. I could do 1 plus 0, which is 1. I could do 1 plus 1, which is 2. Or I could do 1 plus 2, which is 3. So the best I could do here is 3. And that's just walking through the system, right? So, you know, the idea here using, you know, a technical directed acyclic graph is, well, for any node X, right, our recurrence relationship is, let's write this in purple, I don't know, D, I won't be able to fit all this on one page. Okay. So we're going to say the longest path to get to a node X equals what? Well, it's 1 plus the maximum of, well, what are my neighbors, right? Because here I knew what my neighbors were because I already drew up the graph. But how would any node know what its neighbors are? Well, it would be D of, all right, we're going to call this D of node J so it's clearer. Right, so if I'm jumping to node J, oh my God, let's just write this out really big because I'm apparently not able to write things clearly. So we're going to say D of j, hence representing that I'm at node j, is going to be 1 plus the max of d of I for all nodes I less than j. So for I less than j. So what I'm basically saying is I'm going to take the longest path to get to d of j is 1 plus the longest path to get to any of the nodes to the left of me, right? Any people that have already been traversed, right? So to get from I to j, to get to this j, so we kind of think of it in reverse, right? Before we were thinking to get from I to j. Now we're thinking to get to j from I, right? Well, we can only jump from i's that are less than j, right? That's this first constraint. And then the second constraint is, well, I has to be less than j, and the value of the absolute value, right? The absolute value of nums of j minus nums of I has to be less than or equal to target, right? So that'll build in the filtering criteria for us, right? So what will happen for any, general set of nodes, like so, and then, maybe this is j. What it's going to do is, in order to find d of j, it's going to look at all possible values that come before it, right? So it'll start here and say, okay, does this thing have a value, an absolute value less than or equal to target, right? So it'll look at this I. If it does, then it'll build the link. All right, then maybe it'll ask the next one, right? Does this thing have a value less than or equal to target? If it does, then it'll build a link. If it doesn't, it won't. This thing less than or equal to target doesn't build a link. If it doesn't, it won't, et cetera, et cetera, et cetera. The idea here is, well, we've already solved, since we're doing things in order, right? We start at the left and we move over, for any d of j, when we look at things that are less than it, d of I, we've already solved that system. Okay, and I guess the way of thinking about this is okay, how do you kind of logically think about this in an example? Well, if you had I don't know, if you had a bunch of people, I guess, right, who told you, who had their systems like this, right? And I don't know, a pyramid scheme, right? So they had their own networks, right? So imagine we just had two people, okay, that could talk to me, and they had their own networks. And I went trying to say, okay, how many friends do you have to your left? How many friends do you have to your left? I'm trying to find how many friends I have to my left. Well, I just have one more friend, right, than however many people this person has to their left, right? I don't need to traverse this whole system to find the number of friends that I have to my left here or the number of friends I have to my left here. What I can instead do is just ask this person, hey, buddy, how many friends do you have to your left, right? How many friends do you have to your left? And I just have one more than that. Hey, how many friends do you have to your left? Oh, I have one more than that, right? And if I'm trying to find the maximum number of friends I have to the left, I would just take one more than the max of this one and this one, right? And this person can play the same game, right? They don't need to figure it all out themselves. All they have to do is ask their first neighbor how many friends they have to their left, right? So this is the kind of the intuitive way you think about dynamic programming, right? You don't need to resolve the whole system because you just kind of think about, well, what's the maximum number of jumps that I can do? Well, it's just 1 plus whatever my neighbor's maximum jumps that they could do. And if they solve that before I ask them, then I just can add that value to what I'm doing, right? I don't need to recalculate the whole thing, right? When I'm here, since I already solved everything to the left, I don't need to go through all these paths again, right? I can just ask them, hey, what's the longest path to get to? I'm going to add one to that, right? So there's an order to this kind of madness here, all right? Now let's see how much I can get on one page here. Okay. So what is the runtime of this approach? Well, it's going to be n squared, right? Because, well, we have to, for each I node, right, we have to go back I less than or equal to j. So we have to go look through all the nodes that are less than it, right? So for every node, we have to look at all the nodes that come before it. So that's n squared. Okay, with that said, let's go ahead and get right into the problem. So I'm going to create this D array. Now we have to be conscious of this case, right? The only thing in here that kind of throws a wrench in our game is that there's some nodes like this that won't have neighbors. So we don't want to make this value 1, right? Because there's nothing to its left, so it's not technically a neighbor, right? Okay, so let's say D is a default dict, lambda 0. And then what we'll do is we'll look at all I values, or no, we'll call them J values in range length of target, right? Okay, I'm trying to think about how we're going to do this on the fly. And then we can just say this, right? So it's literally just this. We go through each node and play this game. So let's say D of J equals 1 plus max D of I for I is less than or equal to J in absolute value. So we'll just do that. So this I is less than J is going to be built in. So we're going to say for I in range J, right? So that's literally just this. For I is less than J, for I in range J. So that's the equivalent Python code here. We're going to say D of J equals the maximum of 1 plus the maximum. So I'm going to try to make it look more like the formula. D of I for I is in range J. So that's D of J equals 1 plus the maximum D of I for range I less than or equal to J. And then this condition needs to be true. So we're going to say if D of, the absolute value of target of nums of J minus nums of I is less than or equal to target. This absolute value goes over here. I'm very tired today, so I'm doing very strange things that I normally wouldn't. Okay. And then at the end, we would return the last value, right? Because we want to know if we can get to this. Now, there's some, because we could not be able to get to the end, so this is not going to work, right? There's still some conditions here. What if this max stream is empty? Or what if there's nothing that's less than or equal to target? So then this should be 0. So we could do a default value here. So there's some edge cases here that are making this. I already know how to solve it, of course, what an arrogant asshole I am. I can already solve this, but it's weird because there's some edge cases that can make the code kind of funky, right? So what I don't want to do, right, I'll show you what I mean. So this code will happen is if there's nothing, the default value will be -1. So then it'll set this to -1, so 1 plus 1 is 0, so then D of J will be 0, which is kind of what we want here. But if the value is 0, then the answer should be -1. So then we'll say if yeah, this is gonna get ugly. If this, or I think J is the last value. If D of J not equals 0, else -1, right? So if it's 0 at the end, that means there was nothing that could get there, right? Why'd I do length of target? Length of nums, right? We're going through all the nums. Okay, but you're going to notice that this could error out. I'm thinking about a scenario. There's only one node. All right, so this is wrong. Yeah. Okay, this is wrong for a different reason. So what am I doing wrong here? So, let me think for a second. This is good debugging. The J value might not be right here. It's supposed to be length of nums -1. Let's just do that. Not think about. Can't believe I'm getting this wrong. What am I doing wrong here, guys? It's so weird that this doesn't really seem like... So let's print D here, because that's kind of the meat of this problem, right? So what am I doing wrong here? So in this example, you know, 0 should be 0, 1 should be 0, 2 should be 1, 3 should not be 1, 3 should be 0. Because this should not have anything, nothing can get here except for 1. Right? Only 2 can get to 3. So then why is it... Oh, okay. The problem is it's attaching itself to 2 because 2 has a length of 0. Oh, man. I got to rethink about how I'm going to do this. Okay, so let's say D of 0 equals 0. So we can only use a path if its value is not -1. All right, I'm starting to think I might be able to do this better. So, you know, sometimes when you have the right idea, even though you have the right idea, you know, the way that you code it can be very particular, and you need to think about how you're going to make that work, right? So we'll do 1 plus... So we can only make this work, right, if... We can only make this work if the value is good, but also d of I has to be greater than or equal to 0. Well, if it doesn't get set, it'll be -1. No, that'll make it 0. Okay. Ah, guys, help me! D of I greater or equal to 0. And for some reason, I put that right in between everything like an idiot, because I am panicking now. Okay. And d of I greater than or equal to 0. Now, this will create another issue, I think. Yeah, if max is an empty sequence, then we could do default value here. Default value equals -2, because -2 plus 1. I did this another way, and it worked, and it was simpler. You have to start at 1 at that case. Oh my god. Okay, so I did this before, and it worked, and I don't think it was this complicated. So what did I do before that I stumbled upon? Oh, so I did it a longer way, which made it a little bit more verbose, so it was easier to handle, right? This is a shorter solution, so it's kind of messier, because I was trying to make it fit this form. So that's a kind of a lesson in itself, right? Sometimes if you go down a path, even if you have the right idea, right, the solution can become more complicated because you're constraining yourself by the way that you write your code, right? So I'm going to make this thing shorter by doing it like this. How about that? Boom, son. All right, so what's the run and space complexity of this? So n is equals length of nums, of course. So for time, well, we have to look at all j values and then all I values for all j values, right? So that means we have to look at, for all j values, we have to look at all the values that are less than j. So for 1, we have to look at 0 and 1. For 2, we have to look at 0, 1, 2. Then 3, we have to look at 0, 1, 2, 3. Then 4, we have to look at 0, 1, 2, 3, 4. And 5, 0, 1, 2, 3, 4, 5. So that's n squared, right? And if that doesn't make sense, it's just something to memorize, right? If you have a for loop within a for loop, and for each index iteration of the for loop, you look at everything that's less than that index, that is O of n squared, okay? And then space, well, we create this D array, which is of size n, right? Because it's the length of nums. And then for, these two loops, we're just updating D. So that means D is just the size of n, so that's big O of n. All right, guys. Pretty rusty video. It's been a while, but I'm trying to get back into the swing of things. I always say that. Then I spend, 12 to 15 days in between each consecutive upload. Peace out.